Welcome back for Lecture 11, where we're going to give an introduction to probability. So let's start by looking at random phenomena and what is going to happen. And instead of just giving a formal definition of what a random phenomenon is, we're going to do this by example. So let's suppose that we're driving home from work. And you drive through the same intersection every day, and you never know whether the light's going to be red, yellow, or green when you get there. This is an example of a random phenomenon. Formally, a random phenomenon is a situation in which the possible outcomes are known, but we don't know exactly what's going to happen. Each occasion on which we observe a random phenomenon is known as a trial. And what occurs during each trial is known as an outcome. So on the traffic light example, we have three possible outcomes: red, yellow, or green. Red, yellow, and green gives an example of what we call a sample space, or a set of all possible outcomes for a trial. For example, if the light is yellow, you might accelerate and go through it and treat it like a green light. Or you might hit the brakes, treat it more like a red light. You may want to combine the yellow with either the red or the green. A combination of outcomes in this way is known as an event, or what we also know as a subset of the sample space. We'll denote the sample space by the bold-faced S for the rest of this lecture. Let's look at the law of large numbers and what happens if we do a whole bunch of trials. So the question is, what is the probability that the light is green at this intersection? How can we think about it? Well, the important principle is called the law of large numbers. And what it says is that if we repeat a random phenomenon over and over, the percentage of the time, or the proportion of times that the event occurs, settles around a particular number. And this number that the proportion of times the event occurs settles around is known as the probability of the event. So we have some conditions that we need for the law of large numbers. The first and foremost, the most important, is that the outcomes have the same probabilities for each trial, and that each trial is carried out independently. So to summarize, the law of large numbers tells us that as the number of independent trials gets large, the long-run relative frequency of the repeated events gets closer to a single value, that is, the probability of the event. So let's look at the law of large numbers versus the often stated law of averages. So what do people mean when they say law of averages? We hear about it all the time. For example, Mike Trout of the LA Angels is batting .325 for the season, but hasn't gotten a base hit in 35 consecutive at-bats. Announcers often say the law of averages says he's due for a hit. Well, they mean the law of large numbers, first of all. But the law of large numbers doesn't say anything about short-term behavior. It only refers to long-run relative frequencies. So in other words, when they say Mike Trout is due for a hit, no, he's not. If we assume that the probability of him getting a hit is .325, then over a large number of at-bats, we would expect him to get a hit 32.5% of the time. This doesn't mean that he's owed a hit this time because he hasn't had one in a while. So how do we model probability? How do we describe random phenomena? Well, we have several types of probability. Sometimes probability comes from a mathematical model and is not necessarily from observation. We call this a theoretical probability. Common models are based on games of chance. And sometimes people will even assign probabilities to events based on personal feelings. So for example, you might say, if you're taking a particular course, I have a 45% chance of getting an A in this course. This is based on a personal feeling and not on observation. You haven't taken the course a lot of times to be able to observe some sort of long-run behavior. These are personal or subjective probabilities because they're not based on observation, they're just based on subjective ideals and personal feelings. So the message is, when you hear a probability stated, you need to try to think about what kind of probability it is. So when we work with probabilities, we need to sort some things out in order to isolate events and things of that nature. So it's helpful to make pictures. And the most common types of pictures that we make when we deal with probabilities are known as Venn diagrams. We won't give a formal definition in this lecture, but what we will do is point them out each time we use them. So the first three rules of probability: make a picture, make a picture, make a picture. That sounds familiar. You should make a picture for pretty much everything you do in statistics, but especially when working with probabilities. But there's more rules of probability. In fact, there's 5 more, and we're going to go through the next 5 now. The first rule is that if the probability of an event is 0, the event never occurs. If the probability of an event is 1, the event always occurs. So formally stated, if A is an event, then the probability that A occurs, which we'll write P of A, satisfies this inequality. P of A is between 0 and 1. The second rule, if a random phenomenon has only one possible outcome, it's not very interesting. So we have to distribute the probabilities among the different outcomes a trial might have. So for example, you're reading a book and you're on chapter 3, and there's 3 possible outcomes that are going to happen. Outcome A, you read to the end of the chapter and stop. Outcome B, you read a couple more pages and then stop before the end of the chapter. Or C, you stop reading immediately. Something has to happen. So either A, B, or C in our example must happen. In other words, the probability of something happening is 1. So what we do is we assign probabilities to individual outcomes in such a way that the probability of each outcome, the probabilities of all the outcomes add up to 1. So in other words, the probability of the entire sample space is 1. This is called the probability assignment rule. So formally, for a sample space S, P of S is equal to 1. We have the complement rule. Suppose we have an event A that has probability 0.2 of occurring. And then the 2 possible outcomes are A happens or A doesn't happen. The event that A does not happen is known as the complement of A, and we'll note that with A superscript C. In this case, the sample space is made up of 2 outcomes. A occurs, A doesn't occur. Therefore, the probability that an event does not occur is 1 minus the probability that the event does occur. In other words, the probability of A complement is 1 minus the probability of A. And we call this the complement rule. So let's look at a picture of what the complement rule looks like. Here's a Venn diagram, and the big box represents the sample space. The circle inside the box is A, that represents the outcome A. Everything else in the box represents A complement. So the entire probability in the box is 1. We have the probability of A represented in the circle corresponding to A, and then the probability of A complement represented by everything else. So the probability of A complement then is 1 minus the probability of A. Let's look at an example. If the probability that the traffic light is green when you get there is 0.35, what's the probability that it's not green when we get there? Well, let's let G denote the event that the light is green. Then if we use the complement rule, the probability that the light is not green is the same thing as the probability of G complement, which is 1 minus the probability of G, or 1 minus 0.35, or 0.65. So in other words, to summarize, the probability that the light is not green when we get there is 0.65 by the complement rule. Let's look at what happens if we let G be the event that the light is green and Y be the event that the light is yellow. What is the probability that the light is either green or yellow? Well, we need to ask ourselves some questions first. First, can the light be green and yellow at the same time? Well, no, it can't. When 2 events cannot occur at the same time, these events are said to be disjoint or mutually exclusive. So we have an easy rule for finding probabilities for disjoint events. If 2 events A and B are disjoint, then the probability that one or the other occurs, written P of A cup B, which is read probability of A union B or probability of A or B, is equal just simply to the probability of A plus the probability of B. So here's a Venn diagram for the probability of disjoint events. Again, the big box represents the entire sample space, so there's a probability of 1 corresponding to that whole box. The probability in the circle corresponding to A represents the probability of A. The probability in the circle corresponding to B represents the probability of B. And note that they don't overlap, so the total probability in those 2 circles is just the probability in the one circle plus the probability in the other circle. So let's look at the traffic light example again. Suppose the probability that the light is yellow is 0.2. What's the probability that the light is either green or yellow? Well, we're going to use the addition rule for disjoint events. probability of G or Y is equal to the probability of G plus the probability of Y, or 0.35 plus 0.32, or 0.55. So the probability is either yellow or green with probability 0.55. We can move this rule, we can generalize it to any number of disjoint events. So for example, we can use this to check probability assignments. Suppose A, B, and C are disjoint events. Then the probability that A occurs, or B occurs, or C occurs is just the probability that A occurs plus the probability that B occurs plus the probability that C occurs. What about independent events? We say that two events A and B are independent if the occurrence of A does not have any effect on the probability that B occurs. So for example, if your job requires you to fly from Atlanta to Houston every Monday morning, and the airline's website says that the probability that the flight is on time is 0.85, well, what is the probability that the flight is on time the next 2 weeks? We're going to assume that the two flights occur independently. What this question is asking is, what is the probability that the flight is on time this week and that it's on time next week? So for independent events, this is an easy question to answer. We have a multiplication rule. If two events A and B are independent, then the probability that both A and B occur, which is written P of A cat B, or probability of A intersect B, is given by P of A intersect B is equal to the probability of A times the probability of B. So if we let A be the event that this week's flight is on time, and B be the event that next week's flight is on time, then we have that the probability of A is equal to the probability of B is equal to 0.85. We assume that A and B are independent, right? That the flights occur independently. So the probability that both flights are on time is P of A and B, which is the probability of A times the probability of B, or 0.85 times 0.85, or 0.7225. In probability, there are a bunch of things that can go wrong and several pitfalls that we want to avoid. We want to beware of probabilities that don't add up to 1. We don't want to add probabilities of events if they're not disjoint. And similarly, we don't want to multiply probabilities of events if they're not independent. Don't confuse disjoint and independent. They're not the same thing. Disjoint events cannot be independent by definition because knowing that one occurred tells you that the other one didn't. So the probability, or one event occurring, tells you that the probability of the other one occurring is 0. So disjoint events cannot be independent. Don't make the mistake of using the law of large numbers to describe events in the short term. Remember the Mike Trout example, where that doesn't mean he's due for a hit. And finally, be sure to think about whether or not assuming events are independent is a reasonable thing to do. So in this section, what we've done is we described what random phenomena and probabilities are. We looked at some common rules of probability, and then we described some of the issues that can arise when using probabilities, and we also illustrated some of these things in pictures. This is the end of Lecture 11, and we'll see you back here for Lecture 12.